And welcome back to 15-1 where we're discussing water and its properties. In this podcast, we're just going to clean up our last bit of discussion on some of the unique properties that water has due to its structure. If you recall in the last podcast, we took a look at the fact that water is a very polar molecule. It has a very electronegative oxygen bonded to two hydrogens, and so therefore one side of the water molecule is going to be very negative, the other side is going to be very positive, and so water is going to tend to stick together and have a very high surface tension, simply meaning that the attraction between water molecules is fairly hard to break. Now, I didn't mention this in the last podcast, but if you picture water, the surface of water, like so, and the water is attracted to one another like so, these attractive forces are fairly hard to break compared to other attractive forces among other molecules. And so what happens is, say on a very calm day, you can have, say, bugs, and this will be my bug, that can walk across the surface of the water. We'll put wings on them, I guess, something like that. And the reason why this bug can walk across the water is because the hydrogen bonding between the water molecules is strong enough to support the mass or the distribution of the mass of the bugs as it's moving across the surface of the water. All right. Now, surface tension doesn't only have to do with bugs walking across it. It simply has to do with the molecules sticking together. So the fact that water beads up into tiny balls on different surfaces is a result of its high surface tension. We also talked about the fact that water has a low vapor pressure, meaning few water molecules, or fewer than expected water molecules, would escape into the gaseous phase, simply because the water molecules stick together and tend to hold each other down into the liquid phase. So though you would expect water for its size to have a very, very high vapor pressure, it doesn't. It has a low vapor pressure. The last thing we want to talk about is what happens to water as it freezes into the solid state. As it turns out, water, many of you know this, water will expand as it freezes. Ice is less dense than water. Now, why is that? Well, if you can look at this particular diagram here, you can see that when water freezes, it forms these intricate ring structures, and there's a lot of empty space created as they line up. When water is cooling down, first of all, water will be relatively far apart. Okay, so we'll draw it something like this. So on and so forth. As it freezes, or as it cools down anyway, the water molecules will tend to bunch up, and they can fit inside of one another. So if we put it something like this, you can pack a lot of water molecules together by simply zigzagging them back and forth and fitting themselves in the little nooks and crannies. So you can get them fairly tightly packed. However, once they start to freeze, what happens is the water molecules line up in these ring structures, and these ring structures spread themselves out. So where in this particular arrangement there's very few gaps, the water molecules are filling the gaps, as it freezes, it starts to create larger and larger gaps. And so water expands. And in fact, the structure of the ice is a regular open framework of water molecules that's arranged like a honeycomb. If you can think of the honeycomb shape inside of a beehive. All right. And so this expansion is very, very important because it makes ice less dense than water. If I scroll down here, take a look at what happens to the density of water. Of course, as you cool down, the density of the water is going to increase. And that's typical of a liquid. As you cool a liquid down, the molecules get closer and closer together. So it's supposed to get more and more dense. Now, typically what happens is as that substance freezes, the molecules get even closer together, and the solid phase is more dense than the liquid. But what actually happens is that water reaches a maximum density at about 4 degrees Celsius. And at that point, it starts to expand as the water molecules line up into that honeycomb shape. So the most dense water is going to be 4 degrees Celsius, and then it's going to expand. And notice that the density of ice at 0 degrees Celsius is going to be less dense than water at any other temperature. And so because of that, ice is going to float. So what ends up happening, if we draw, say, a surface of some water here, in the wintertime, the surface of the water starts to cool down. And as this cools down, this dense water starts to sink to the bottom. So the coldest water sits on the bottom of the lake. The warmer water gets pushed up to the surface. Well, that starts to cool down, and that water is going to start to sink. And eventually what happens is you have this layer of very, very cold, dense water at the bottom at 4 degrees Celsius. At the top, because that coldest water is already sitting at the bottom, more water is not necessarily going to sink and replace that. So eventually what happens is you get a layer of ice that forms on top. But because that ice is less dense than any of the other water, it sits on top, and eventually what you can get a freezing where it freezes a little bit deeper and a little bit deeper, something like this. However, eventually what's going to happen is there's going to be a buffer area here where you have the coldest water sitting on the bottom, and then you have the ice layer on top, and you have a whole region where organisms can live. Alright? That's just one of. Now, if this did not happen, what would end up happening is the ice would sink to the bottom, which it does not, and then you would get an ice layer that fills from the bottom up. There would be no area for the organisms to live, and life as we know it would not exist. It's not to say that things wouldn't evolve a different way, but the current systems that we have would be non-existent. Okay, all right. So that concludes 15-1.